to Muhammad Gulzari from the School of Civil Engineering. This is an area I know very little about. He's going to talk about acoustic and mechanical metamaterials. So I'll not attempt to make myself look silly and try and say anything more about it, but I'll let him talk a bit about himself. Recently joined UCD, having been in, he's been in a few institutions around this country before, but I'll let him give a little more introduction about himself and then get on with his presentation. So thanks very much, Mohammed.
Thanks everyone. Thanks, Will, for organizing this, and thanks everybody to coming here physically and virtually. My name is Muhammad, and my PhD is from City University of Hong Kong. I came to Ireland on Irish Research Council postdoctoral fellowship, joined Trinity College Dublin Department of Mechanical Engineering. I'm a civil engineer. For past 3 years in Ireland, I'm working in mechanical engineering department. After 3 years of struggling, I luckily landed back to civil engineering. So I work in Trinity first year as a research fellow. In the second year, I was working as an adjunct assistant professor. And then I get an employment at University of Galway, Department of Mechanical Engineering. For about a year, I was working there. And in July 2024, recently, I moved to UCD and started working as assistant professor in the School of Civil Engineering. So my area of research is acoustic and mechanical metamaterials. And I will try to be less jargonic, use less technical terms, and try to explore this area, which might be new to most of you, but it's a very fascinating area because it's very much multidisciplinary and hard in nature. So this is my talk outline. I will first of all talk about what is acoustic metamaterials and mechanical metamaterials very briefly. Then I will tell you more about some of the acoustic and mechanical properties in less technical terms that is exhibited by the metamaterials. Then acoustic metamaterials application, mechanical metamaterials, and their application in a wide range of disciplines. So metamaterials in itself, it's not a material. These are artificially engineered structures. So we design these structures on a different scale. People in electromagnetic fields, they are doing it for antenna purposes at nanoscale or on micro scale. People in acoustics are doing this at the millimeter scale or micrometer scale or even meter scale. So we really play in acoustic metamaterials field, we play with the frequency and the size of the structure. So we design these structures in such a way that gives some unusual properties that you cannot observe by naturally, that cannot be exhibited by the naturally occurring material. For example, metamaterials give negative permeability and negative permittivity, which is the famous property in electromagnetic field. According to the people who are working in an electrical department or electronics, it might be a little bit confusing for them if you tell them that the negative permittivity, the permittivity and permeability can be a negative number. Generally, it's a positive number. Okay. In acoustics, it can give you negative mass density. It can give you negative bulk modulus. These are some terms which I think you have come across in your higher secondary school if you're not from an engineering background. And it also gives you a negative Poisson ratio property. So Poisson ratio is if you stretch a material in one direction, in longitudinal direction, it contracts in the other direction. And this is a natural phenomena. But if you design your structure in a fascinating way, you can produce negative Poisson ratio, which means that if you stretch your material in longitudinal direction, it will expand in the lateral direction. And if you compress it in the longitudinal direction, it will compress on the other direction as well. So these are some unusual properties which are exhibited by the artificially engineered materials. We call them metamaterials. So this is a short description. So these are material which gives unusual property. One of the famous property in acoustics is the band gap. So metamaterials produce frequency band gap. The simple definition of the frequency band gap is anything which is any frequency which is lying inside the band gap cannot propagate through the structure. So it's very good for the isolation of vibration, for noise, or if in fact for applications such as for radar application, that if you want to hide your aeroplane flying in the air and you don't want that your radar catch it, so you use the frequency band gap property, because the principle of the radar and the noise and vibration is all they travel in a medium. And once they interact, they basically back reflect. What if they don't back reflect and attenuate it, then your system cannot detect. So this is one application. So frequency band gap is a famous thing, except that it can give wave guiding. So you can guide your waves. By waves, I mean acoustics, elastic, electromagnetic, optic, microwave. So all the waves are coming under this category. So it can do wave guiding. It can give negative refraction property. It can be used for super lenses, and it can also use for seismic shielding application, a very good application. And my PhD work was on seismic metamaterials. So we put structures surrounding the buildings, important infrastructure. And when the earthquake is coming, they also have hazardous frequency waves. So when they interact with these metamaterials, they basically protect the main structure from the earthquake. So you don't disturb the foundation, but you protect your structure, atomic power plant, museums, any big infrastructure. Now, in terms of noise and vibration, this was one of the active area that I was pursuing. You can see that noise and vibration is almost everywhere. And this is a serious problem. So in order to solve this problem, we have metamaterials into action. And there are different types of the metamaterials based on their different property. For example, this is called plate type metamaterials, which is very famous in giving negative mass density property. So these are very thin films, thin panels. And these thin panels are artificially designed. If you put them on the window or anywhere, they can absorb or attenuate the incoming sound waves of very low frequency. For example, if you need a 2 meter or 1 meter thick foam to reduce the noise, that can be replaced with 2 millimeter or 10 millimeter thick panel to reduce the same noise, but much more effectively. So this is one application. The second is membrane type acoustic metamaterials. These are membranes, which is very similar to our air drum. So we put a mass, and then this can be used for different application, especially in aerospace industry, to basically isolate low frequency noise. So the size of the structure is very small, and it can basically cater very, very high, very low frequency or very high wavelength acoustic waves. The third is the MPPs, micro perforated panels. These are very small holes which you make on your plate. And this is used actively at the moment in US in the aerospace structure to reduce the noise on the aeroplane wings. So you just make small holes and you design those holes, which are called MPPs, micro perforated panels, and they absorb very low frequency noise. So very good for aerospace application. This is origami programming acoustic metamaterials. You can program what frequency it should work, what frequency it should not work to attenuate. And this ventilated acoustic metamaterial is widely used for the AC ducts, which is giving huge amount of the noise in the industrial area. So we put these structures just beside the ducts, which are very small, very thin, and they reduce those noise. And this is the periodic pile barrier. At the moment, it's applied in China in one of the projects. So we put piles between the railway train and the housing. So those houses which are close to the railway track, we put piles of the barrier. We make piles, and those piles reduce the vibration which is generated by the railway. Briefly, this is application which is quite broad, and it can be used for vibration control. It can be used for acoustics. Can have good application in automobile, aerospace, civil engineering. You just name it. Wherever you have a noise and vibration problem in one way or other way, it has application because of the frequency band gap property. Now, generally, when we talk about metamaterials, they are classified based on their dynamic and mechanical properties into 4 streams. Electromagnetic is something which people in electrical and electronics might be very much interested. I'm not working in this area. Chiral metamaterials is also coming into their domain. What I am interested is acoustic metamaterials and mechanical metamaterials. Acoustic metamaterials have dynamic, unusual properties, while mechanical metamaterials unusual kinematic properties, such as negative Poisson ratio effect. One good example of mechanical metamaterial is ceramic. If you design your structure with ceramic, ceramic is generally a very highly brittle material. If you load the ceramic, it will break. But if you design your ceramic, if you design structure with ceramic based on the principle of metamaterials, ceramic can be converted from brittle to ductile material. So no longer it will break if you apply a compressive load. So this is some unusual property, and those are some of the application. So in case of mechanical metamaterials, negative Poisson ratio, as I said, Poisson ratio is lateral to lateral to longitudinal contractions. So it gives negative Poisson ratio effect, where your Poisson ratio mu is much less smaller than 0, while your shear modulus is much greater than your bulk modulus. Okay, I'm trying to use the less terms, but I cannot explain this in more general term. Negative elastic or near 0 stiffness property. Stiffness is how strong a material is. When I'm saying negative stiffness, it means the material is very soft, very flexible. Okay. Negative compressibility, means just like water. So you can make solids which behave like water, but it's not a water. So it has a very small shear modulus value, and then ultra lightweight and ultra high strength. I think ceramic is a very good example of this. You make your structure, I will show you in a while in an example that has the Young's modulus divided by a ratio, the density ratio is very large. So you optimize this. And this is the fluid-like solid structure, which is a pentamode lattice, which you can see here. Biomedical is an important field of application for mechanical metamaterials, and it's highly sought. One good example is the multifunctional metamaterials that can be used as a nano generator for energy harvesting, active sensing inside the blood. So there are quite a number of phenomena going on inside our blood veins, and we can put nano chips basically to generate that can be used for sensor to provide some information about clots, about anything happening in our blood veins. So we can design structures in that way. A very famous application is in the bone implants. So when your bone is fractured, for example, the bone plate, generally they are replaced by conventional aluminum alloy plates. And those plates are just solid and they are very heavy, and sometimes they cause infection. But those structures are now being replaced by metamaterials and for the bone implant application. So these are some example. For example, the first one is the lightweight, strong metamaterial. If you design this structure, it's irrespective of the material. If you design the structure with let's say with the ceramic or with polymer, it will give the same mechanical behavior if you plot the load versus deflection curve. So material itself is not an important thing here. Design is very important. This one is auxetic mechanical metamaterial, which means if you design a structure, if you put a number of this structure all together, you compress it, it will compress on the other side as well. You stretch it, it will stretch on the other side as well. And that is pentamode. Pentamode lattice gives negative or near zero shear modulus. So this is solid, but it behaves like a liquid. Liquid has very small shear modulus or nearly zero shear modulus. And that is chiral metamaterials. Because of the time, I'm conscious of the time. So these are some mechanical application just to make it more interesting. So this is mechanical metamaterial bone screw, back pain. So you put these mechanical metamaterials as a bone screw in between the joints. And the good thing is that it is negative Poisson ratio. So when it's compressed, it compresses on the other side as well. So it will not bulge out, which is very good compared to the conventional one. This is mechanical metamaterial stent. Stent is used especially for the heart surgery and for the veins if there is a blood clotting or anything. So they pass stent in your body to remove. So this stent will initially is very thin. When it goes inside your blood vein, they expand to basically open the vein and then remove the clots. So metamaterials stent, the benefit is it can, if it's expanding in one direction, it's expanding in the other direction as well. If it contracts in one direction, it contracts on the other direction as well, which gives it advantage from the conventional material. And this is the artificial inert vertebral disc replacement. So you can replace the conventional disc with the metamaterial disc, which we can see here. The other application is meta implant, and this is the stem of the artificial joint, which is prepared by mechanical metamaterials. This is the additive manufacturing technology is used. And this is the self-aware metamaterial implant, which means it has electronics feature as well. So it goes into the body, and based on some piezoelectric effect, it can also give some signal about your body, what's going on. And so this is the alloyed orthopedic implant, which is generally used in the orthopedic surgery very much. This is the prototype of the hip implant, which is this part. Okay, so this side that you can see, I don't know if I can use the pointer. This side that you see, this is a negative Poisson ratio material. On the other side, it's a conventional material. So when this hip is under the compressive load, the negative Poisson ratio one will basically shrink on both sides. So it will not interact with the tissue, and you will not have a tissue infection, which is a major problem in case of these hip implant currently dealt by the biomedical people. And this is the future that we are looking for. So we are going to design lightweight, but very strong materials, which gives very unusual mechanical properties that cannot be achieved from the normal material. For example, we can change the nature, the normal behavior of the material. For example, ceramic, concrete, they are highly brittle, but we can make them ductile in a way. Okay? Another good application is bone fracture. So if you go to the normal surgery, you will get a normal plaster, which you put on your bone in case of any injury, but that can be replaced with the metamaterial. So you can put this bone implant, or in fact, for the bigger part as well, you can develop this metamaterial stuff that can be very lightweight. Also, it helps in recovery. So you can move your arm, your shoulder very much freely, because with each movement, these unit cell structures, they configure themselves so that to give you more comfort. How much time I have, Will? Okay, so these are some potential application. Now, it was more biomedical thing, because at the moment, mechanical metamaterials is highly sought in biomedical because of the its promising application, but its application is not limited to biomedical. It has also application in automobile, in aerospace industries as well. For example, the lightweight metamaterials, by lightweight, I mean it's very light, but it's very strong. If you compare the same material, one with metamaterial design and the other with just simple design or no design, and you put them under the machine, they will give even much better performance than the other one. So the lightweight are primarily used in aerospace, automobile, and construction application, where they improve the fuel efficiency of aeroplane, automobile, and reduce the self-weight. So you reduce the weight, you increase the strength, and that's the challenge. Pattern transformation. So it transforms its pattern based on the application. For example, for the bone recovery, you basically make a pattern transformation material. So once you open your arm, close your arm, it will change the pattern. If your bone is broken somewhere here, based on that pattern, it will give you somehow comfort. Mainly used in the field of vibration isolation, energy absorption, and the negative compression one is widely used in mulfing and vibration prevention, which can also be used for the sound insulation. So this pentamode one is used in the field of telecommunication and sensors, because it is solid but behaving like a fluid, which can be improve the performance and capacity of the telecommunication system, as well as sensitivity and response of the or speed of the sensor. That sensor can be used for the bridge or for human or for aeroplane, for any application. And auxetic or auxeticity is basically the effect that a material is giving negative Poisson ratio. And they have huge amount of application. Wherever you want that you should have a negative Poisson ratio effect, for example, based on desirable application, you can design. So it's not field specific. So in biomedical, these lightweight metamaterials and auxetic metamaterials are more common used in bone implants and the vascular stent design, which is very popular at the moment, and this is highly sought. Because of the because of the time, I'm going to skip these slides, but because I'm already over time, I can answer this basically in question. Now, this is an important slide. Usually, what we do in mechanical metamaterials, I should have showed this in the acoustic, but it's more or less the same. So it's more about the modeling. We model these structures based on some theories, and then we simulate them to validate those theories. And then we pass it to the material design part, where we design the material to work based on the theory and simulation. And then we optimize it based on genetic algorithm or topology optimization, machine learning, deep learning, whatever you can call it. And then we pass it to the additive manufacturing or laser cutting or the technology to fabricate them and test them. At the moment, it is more in TRL1 to TRL4, but now it's moving towards TRL5 and TRL6 as well. If you check the ERC website, you will find that almost every twice a year or every year, you will see the idea on metamaterials is funded. A very good example is if you go to the Google search UK Metamaterials Network, UK government in itself has established in 2019 the UK Metamaterials Network, and this network is very established, and they are funding quite a lot of projects on this idea because of the potentiality of these ideas. So currently, I'm working in here in UCD on this idea, and there are very few people. So hopefully we will expand this network. At the moment, there is the Irish Acoustic Metamaterials Network, IAMN, which I proposed to establish with the IRC New Foundation. So if it's successful, that is the next step, that we will establish Irish Acoustic Metamaterials Network, and that network will link with the US, UK, and mainstream EU partners to basically further expand this idea. So metamaterials is really not a specific field idea or topic. It's very multidisciplinary. We have people from physics, material science, mathematics, engineering, and it's open for more exploration. I will stop here, and if there is any question, I'm happy to take the questions. Thank you.